Hello, in this video we are going to discuss the bounce diagram in the frequency domain. That's addendum 2C, part of chapter 2, transmission lines. Before I get into the details of this addendum, let me just say that the bounce diagram indicates that we are looking at a transient, things bouncing back and forth in time. And when we say frequency domain, we're talking about harmonics in the steady state. The mix of a transient and a steady state here is kind of maybe confusing, but we'll see how it goes. However, if you are confused about it, I suggest you go to addendum 2D and read that first and study it, and then come back here. However, I suggest that you go over this once first before you do that. Alright. The concept of a bounce diagram of a frequency domain, we're thinking here about a harmonic that we just switched on at t is equal to 0, as if we have a switch here that we just turned on, and we're looking at the initial launch of this harmonic, and this harmonic will go back and forth bouncing between the load and the source indefinitely. Eventually we reach a steady state, and that's where we get the frequency domain expressions. So the frequency domain expression that we are seeking will be the steady state result of all these multiple reflections. So let's get started and see how it goes. Here's our transmission line, characterized by its own characteristic impedance Z0, a complex propagation constant gamma, a length L. We have a source, harmonic source V sub S, an internal impedance Z sub S, and we have a load Z sub L, a simple transmission line circuit. As we turn on the switch at t is equal to 0, there will be an initial launch right there. We call that A. I'm going to ignore this part here. How much is A? How does it relate to V sub S? We'll talk about that later. This launch will propagate down the line until it gets to the load end. It meets a Z sub L coming from a Z0. There will be a reflection, and the reflection coefficient is determined by the mismatch between these two impedances. Z sub L minus Z0 divided by Z sub L plus Z0. If you recall, that used to be called gamma sub L, uppercase gamma sub L. We are calling it here uppercase rho sub L, for a good reason that we'll explain a little bit later. The first reflection will come back and will meet the characteristic impedance of the source. Again, as a mismatch to the characteristic impedance of the line, there will be a reflection coefficient. Zs minus Z0 divided by Zs plus Z0. That's the reflection coefficient here, and again we are using rho instead of gamma. So these are the two reflection coefficients, the one at the source and one at the load. As the signal go back and forth, is going to get modified by these reflections. It's going to also be modified by the travel from the source to the load and back again from the load to the source. As the signal travels from one side of the line to the other end, it gets modified by e to the minus gamma, the distance traveled. This is the expression that we saw in the body of the chapter, e to the minus gamma times the distance. Well, the distance here is L, so e to the minus gamma L is the modification of the signal coming from the source to the load. Also coming from the load to the source is going to be modified by the same amount. This amount here is going to be called T in our development. So we're going to use the symbol T to indicate that modification. So if we start with a signal here launched at the beginning of the line as A, when it arrives here is going to be A times T. Gets multiplied by this reflection coefficient. What comes back here is going to be the rho sub L times A times T. Rho sub L times A times T. that signal travels this way, and by the time it reaches the other end, which is the source end, it gets modified again by e to the minus gamma L. So there's another t here. So it becomes rho sub L times A times t squared. Hits that reflection here, rho sub S comes back, so what comes back is going to be rho sub S times that. Alright, the diagram is going to get messy here if we write all these expressions here, and you can imagine that there are so many of them as time goes on, so we need to establish that in a graphical form, and that's what we're going to do here in this diagram, the one on the left here. Here's our A, and here's AT, the first arrival. Here's rho L times AT, the first reflection. Rho L times AT squared, the arrival at the source. Rho S rho L AT squared is what gets reflected here. And again, rho S rho L AT cubed now as a result of T multiplied through that propagation. And here's another reflection. So this signal gets multiplied by another rho sub L. Comes here multiplied by another T. Comes here multiplied by another rho sub S. And so on and so forth. What arrives at the load end is simply the sum of these two. Let's highlight that. This is simply AT plus rho L AT, and the result will be 1 plus rho L times AT. Likewise, what arrives at the source end here will be rho L AT squared plus rho S rho L AT squared, adds up to 1 plus rho S times rho L AT squared. What arrives here in the second arrival will be again the sum of these two. Here it is. What arrives here at the source end will be the sum of these two, and there it is. So this bounce diagram here continues. Basically, we are doing that in a graphical form between two coordinates here, distance and time. The distance between the source and the load is z, and the end of the line here is L, and this one here is time. The time it takes for the signal to do the first travel or one-way travel, we're going to call that tau. Tau is the time here it takes a signal to do one-way travel. A two-way travel, by the time it comes back here, will be 2 tau. So this is 2 tau. Where tau is basically the length of the line divided by the phase velocity, L over C. So the first arrival here will be after 1 tau. There it is. The first arrival or first reflection coming back at the source end will be after 2 tau. Back and forth. 2 tau. So this is actually 3 tau. And this one here is 4 tau, and so on and so forth. So where is our frequency domain expression? Basically, the steady state will be all of these added together, because this is not going to stop. That's a harmonic. So the source keeps sending sine waves. The source keeps sending sine waves, so this exists at all time. Yes, we saw the first initial value of it, but it continues to exist. This continues to exist, this continues. So in the steady state, all of these add up. 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 So where is our frequency domain expression? Basically, the steady state will be all of these added together, because this is not going to stop. That's a harmonic. So the source keeps sending sine waves. The source keeps sending sine waves, so this exists at all time. Yes, we saw the first initial value of it, but it continues to exist. This continues to exist, this continues. So in the steady state, all of these add up. 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 We're going to summarize that in the table down here. Let's look at the load end first. At the load end, the first arrival is right here. Let's highlight that with a different color. Right there. At the load end, the first arrival is right there. Second arrival, right there. I can predict the third arrival and the fourth arrival, etc. And if you notice, this is nothing but a geometric series. And the geometric series adds up to this expression here. So actually this is your frequency domain expression of what gets to the load end in the steady state. Let's look at the source end, different color. At the source end we have the A first, here it is, and then we have a signal coming back from the load, there it is, a second arrival, there it is, and I can actually predict what the others, because again it's a geometric series starting with this term, the A plus a geometric series. If you really worked out, you can come up with this expression. That's what you get. So as you can see, I was able to derive the voltage at the source and the voltage at the load simply by doing this graph. If you recall, in the body of the chapter, it was kind of difficult or a little bit more involved to do it analytically. This way here is much quicker. If you want to get the voltage at some location in the middle, let's use a different color. Somewhere in the middle here, what is the expression for the signal? Again, we do the same exact bounce diagram, but we just monitor the signal at locations in between. The A here, when it arrives at this location, is going to be modified by e to the minus gamma this distance only. So I'm going to call this one here T sub z. And T sub z will be just like the T was. The T was e to the minus gamma L. The T sub z will be e to the minus gamma z. If I want to look at the signal coming back from this way, the propagation this way will be T sub d, which is e to the minus gamma d. So I can simply take this expression here multiplied by T sub z to get that. I take this expression multiplied by T sub d to get that. This expression here multiplied by T sub z. This expression here multiplied by T sub d. And so on and so forth. So I can look at this location and write all the positive waves and all the negative waves. And here it is. Let's just label them or highlight them. Let's just highlight them. This one here is the first at location z, at sub z. The second one is rho s rho l at squared t sub z, rho s rho l at squared t sub z. The third one is right there. The third one is right there. If I want to look at the ones coming back, this one here first, rho L A T T sub D, rho L A T T sub D. The second one is right there. The second one is right there. And the third one and the fourth one, etc. And again, these are geometric series. They add up. So actually you can get yourself V plus of Z and V minus of Z right there. Again, it's done in a graphical way, and it's not as complicated as the analytical method that we used in the body of the chapter. Now let's get back to decide about the A. Remember, we said we'll defer that part until later on. The A is the initial launch. And this initial launch is basically when you first turn on the switch and the signal leaves the source and goes down the transmission line. It hasn't seen the end of the line yet. So the input impedance here now is that of a long line, an infinite line, nothing at the end of it. So this impedance here looking into the line is actually Z sub naught. So what you see here, the signal here, will be the V sub S divided, voltage divider between Z sub naught and Z sub S. And here's the expression. The A is V at Z is equal to 0, also at T is equal to 0. So it's actually Vs times Z naught divided by Z naught plus Zs. That's your A. Very simple expression. Now, why did we call this rho instead of using the gamma? We get to this diagram here. This diagram here explains why. The gamma was basically the ratio between, at any location on the line here, between the reflected signal and the incident signal. So it was V minus over V plus. Actually, the gamma of Z is the ratio between this V minus and the V plus. If you divide these by each other, you don't get simply rho of Z, because there's no such thing. The rho is basically the instantaneous reflection at the local discontinuity. There's no discontinuity at this point here, so there's no instantaneous reflection. The signal doesn't get reflected here. The signal gets reflected here. So the physical reflection happens here. And rho sub L is the physical reflection at the discontinuity. Gamma, the one that we used before, was a mathematical expression, ratio between V minus and V plus, and it does not represent an instantaneous or a local reflection at this location. Rho sub L, however, represents that, the actual reflection here. At this location here, rho sub L is simply the mismatch between ZL and Z naught. That's why we use uppercase rho. As we go in the time domain, which is going to be explained in addendum 2D, you will notice that we are using rho sub L as a lowercase rho. So that's why we use an uppercase here, because typically we represent frequency domain terms as uppercase and time domain term as lowercase. So the rho sub L in the time domain was a lowercase rho. The uppercase rho sub L here is the frequency domain one. So let me fix that here. I used a lowercase rho here. Alright, it actually should have been an uppercase rho. And this one as well should have been an uppercase rho. And actually that's what we used in the diagram here. We used an uppercase rho and uppercase rho. Okay? Now, like I said, you may want to go to addendum 2D, look at that, and come back here again. Hopefully you will feel comfortable with this approach and you'll find it useful, because it's like a shortcut that gets you the answer much quicker than doing the analytical expressions and looking at the boundary conditions and V plus and V minus and resulting into how much is the voltage here, how much is the voltage there, and how much. All these kind of things get a little bit tedious using the analytical expression, while here it's kind of intuitive and gets you there much quicker and with more physical insight of what these expressions are about. That's the end of this discussion here. I'll see you in another video.